Thank you, everyone. I hope everybody is enjoying nice weather of New Zealand. Uh, in this talk, I'll be presenting C2 Check C by 3C. This is a collaborative research done with other fantastic people from Amazon, but the work has been done prior to moving into Amazon. So it's 2022, we still have memory issue. Memory safety is still a problem, especially in embedded operating systems, which are predominantly still written in C. Our analysis shows that 68% of vulnerabilities are still spatial safety violations, basically buffer overread and underread. Recent bugs in OpenSSL, I don't know if you are aware of these things. These are spatial buffer overflows, specifically Heap buffer overreads. Okay. Here, as you can see, although developer tried to make do the check, but the check was slightly wrong, because of which the code was able to read 4 bytes more. And these bugs can be hard to spot. For instance, this is a bug in UEFI driver. Here, although there is a check at the beginning, but the second clause reads 4 bytes more than the check, which checks for whether we have space for 1 byte more. So the checks are hard to do, and violations are there. But this problem has been looked upon for quite some time. So there are a bunch of works that tries to add memory safety to C. So at one extreme, we have high-performance safe languages like Rust and Go, where they provide more guarantees by completely rewriting C to this new language. But there is a huge amount of development effort if you have to port legacy code into these languages. Furthermore, the support for embedded systems is not well explored in these high-performance languages. At the other extreme, we have automated techniques like ASAN, which had a lot of performance overhead, making them almost impossible to use on resource-constrained embedded devices. In this work, we focus on Checked C. So Checked C provides best of the both worlds. So it provides spatial safety with almost no performance overhead. In addition, Checked C also provides backward compatibility, in which you can have parts of the code converted to Checked C and still enjoy memory safety on those parts of the code that you have converted. So let's do a quick primer of Checked C. So how many of you know Checked C? How many of you heard of Checked C? Okay, I see 3 slides. Good. So for the rest of you, this might be a primer, but believe me, you like it. So Checked C provides 3 basic pointers, okay? Pointer, array pointer, and anti-array pointer. So pointers, the annotation pointer says the corresponding variable is a pointer to an object of type T. Array pointer means it's a pointer to an array of type T. Anti-array pointer is a pointer. It's same as array pointer, but it's just that the pointer is null terminated. Basically, at the end, you have a null byte. Once you add these annotations, what does Checked C gives? Checked C gives guarantees. The pointers that were annotated don't have any spatial safety violations. How does it provide? It tries to do this statically. However, in few cases where it cannot do statically, it adds runtime checks, but without any extra metadata, so that the code or the pointers are compatible with the existing C pointers, which do not contain any metadata anyways. So to give an example, here we have a pointer annotation. So as I mentioned before, pointer is a pointer to a single object. The way you annotate the pointer is as shown on the slide. So when we write this code, basically this is simple C code, except for the additional annotation we did to the pointer. Once we write it and compile using Checked C compiler, Checked C compiler adds a runtime check to make sure that the pointer P that you are accessing is not null. And it disallows any pointer arithmetic on a variable that is declared as pointer. So here you will get a compilation error. Type checker will scream at you so that you avoid this. What about array pointers? Array pointers, as I mentioned before, it's a pointer to an array of elements. And array pointer has a bounds declaration which defines the bounds of the array, basically how many elements the array contains. So, but you can declare an array without bounds, in which case, if you try to access it, compiler will scream at you saying that it doesn't know the bounds of the array. So if you're trying to access it, it says that it's out of bounds access. But you can give bounds. There are 3 ways to give bounds. One way is using count. So count, and you can give bounds expression using count annotation. Note that the bounds expression can be any arbitrary non-modifying expression. It need not be constant. It can be a variable as well. So once we add bounds annotation, all accesses will be now checked. For accesses that can be statically checked to be safe, compiler is happy. For checks that are obviously violating, compiler screams at you saying that it's an out-of-bounds access. For checks that cannot be proved statically, in either case, we add a dynamic check. So note that the bounds are correlated using the bounds annotation. It doesn't matter what type of the size of the object that you point to. We always, or rather Check-C always use the annotation provided by the developer. Here, in the second declaration, we can see that P actually points to an array of size 30 elements. However, the annotation says that the bounds are only 15 elements. So when we have a access P of 15, which is one byte beyond the declared bounds, compiler will throw an error. Although this is not an error because it's actually the access is within the bounds, but since the declaration defines the bounds to be 15 elements, compiler throws an error. And when we have assignments and when we are trying to artificially increase the bounds, compiler will figure it out and it will throw an error saying that the declared bounds are actually invalid after reassignment. Okay. So there are other ways to declare bounds. There is bounds annotation, which provides lower bound and upper bound, which are basically absolute addresses that define the range of the array pointed by the corresponding variable. So here, the same case happens when we are trying to access using this pointer. A check is made. Again, if it can be discharged statically, error will be thrown. If not, a dynamic check will be added. So null terminated arrays are similar to arrays. It's just that null terminated array at the end, you have a null byte. An interesting part of null terminated array is automated bounds extension. So when we have a code as shown at the bottom, Check-C automatically extends the bounds by 1 byte because it now knows that the last byte is not null. So that next time when you access it, it allows you to access one more element. Now, after the second check, the bounds has been extended by one more element. The third is invalid because the bounds is actually 2, but here we are trying to access one more element. Okay. So there are other very good Check-C features that enables the code, the Check-C code to be backward compatible with other C code. Okay. We have I-types that enables header functions to be called by Check-C code. We have checked and unchecked regions that enables disabling certain checks in certain regions of code. We have dynamic bounds cast, assume bounds cast that force casting to checked pointers from regular C pointers. But converting C to Check-C is not free. You still need to provide these annotations, right? And these annotations should be done carefully because if you provide wrong annotations, compiler will scream at you. So you don't want to do that. So for simple programs, most of the changes are easy. Like most of the times, you just need to provide annotations. Whereas for complex programs, like FreeBSD kernel, where this was a recent work where at University of Rochester, they tried to convert part of FreeBSD kernel, basically the MBOF interface, into Check-C. Here, it took 2 undergraduate students approximately 3 months to do the conversion. And given that most of the changes are easy modifications, our problem is, can we automate this? Can we automatically convert given C code to Check-C code safely? Or rather, we don't want to just randomly add annotations. We want to make sure that we add annotations according to the type system that Check-C provides. But not all pointers can be converted to Check-C. For instance, if you have invalid casts, Check-C don't support these invalid casts. So these pointers, of course, cannot be converted. To make things more complex, there are some artifacts which are not supported by Check-C. For instance, in bounds expression, you cannot use a modifying expression. So that means you cannot have a pointer dereference in a bounds expression. So a code which is on the left-hand side, if you have to convert to checked C variant, you need to add, one way is to modify buffer and put it in a structure. But doing that, in order to do that, you need to refactor all the colors of resize buff. It just adds a lot of complexity. So the conversion, so the automated conversion is not that easy. We give up. We say, okay, we accept the defeat. We know automated conversion is not possible. What do we do instead? We resort to human in the loop approach. So our goal is, given the source code, we try to infer checked types for most of the pointers in an automated way. For pointers where we cannot infer the checked types, we find the root causes why we failed, and we ask developer for assistance. Developer can fix those root causes and run our tool again, so on and so forth, until developer is satisfied with the conversion, and we get the fully ported checked C code. Note that this has to be done only once for a single code base. It need not be done every time a code gets modified, right? So you have your code base, you convert to checked C code, and you can just maintain your checked C code without doing this conversion every time. Okay. How do we do that? The automated part has two components. One is types, where our goal is to infer checked C types for pointers. The other component is bounds, which is to infer bounds annotation for array and anti-array pointers. So types, we all know type inference. The basic idea is type qualifier inference. Here, what we can do is we can create qualifier variables for all the pointers, because we want to convert pointers to checked C types. And then we add constraints based on pointer usage. For instance, if there is an assignment, we add a subtyping constraint that the qualifier of R should be subtype of qualifier of M. Okay? So on and so forth. And then we solve the constraints based on the type system of checked C. We want to have the greatest solution or the most general types that satisfy the constraints. We get the corresponding types. Once we have the types inferred, we can do the rewriting. Okay? But if you do the regular qualifier inference, wildness or wild pointers will unnecessarily pollute your constraint graph. For instance, here in this case, a regular flow-sensitive qualifier inference will make pointer y wild, or rather unchecked, although it is used correctly in the function deref. Okay? So ideally, what we want is we want to localize wildness. That means a pointer, we want to make a pointer checked or wild only if it is used unsafely within the function. If a pointer is used completely safely within the function, it should be checked. Okay? For instance, a parameter is wild only if it is used unsafely within that function. So it doesn't matter if a caller passes an unchecked pointer, but if the function uses the parameter in a safe way, we can make that pointer a checked pointer. Similarly, the same reasoning applies for return types as well. So based on this argument, we want to isolate inference across function boundaries. So the obvious solution is to just remove the edges across function boundaries, right? Let's remove the edges. We run the type inference. But if you run the regular type inference, the result that you get is not what we expect, because you lose the constraints across function boundaries. Okay? This doesn't work. And this is conflicting requirements, right? So if we assume all pointers are checked, then we need to propagate the type information across function boundaries. However, if there are wild pointers, we need to isolate them. So there are these two conflicting requirements. The way we handle this is, I think, thanks to Hicks. This was Hicks's idea. Let's split the graph. So why we just need to use one constraint graph? Let's create two sets of constraints. First category of constraint is kind graph, which is where the goal is to identify whether a pointer is a checked pointer or the wild pointer. And the second graph is a pointer graph. Here, the goal is to identify precisely what type of checked pointer it will be if we assume that everything is a checked pointer. And we also split nodes, or rather, we create two sets of constraints. We create two sets of nodes for the function parameters and return values in order to isolate the propagation of wildness. So what happens is we create two graphs. So this is the first graph, kind graph. So here, as you can see, across function boundaries, we restrict the propagation by making the information flow outwards. We don't get any information inside in case of kind graph. We only flow it outwards. Okay? Within the function, we use unification. So as indicated by the blue edge, within the function, it's all unified. As across the function boundaries, it only propagates outwards. Then we solve it by using the subtyping, like check is a subtype of wild. We get the solution. For pointer type graph, we use regular flow-sensitive type qualifiers. We get the corresponding solution. And for the final solution, what we do is we check, for a given pointer, we check what is the kind solution for that pointer. If kind graph says if it's a check pointer, then the final pointer type will be given by the pointer graph. If the kind graph says it's a wild pointer, then it's a regular wild pointer. You just make it a regular wild pointer. So given the kind graph and the pointer graph as shown on the slide, we get the final solution by taking the final type from the pointer graph. If it is a green node, if it's a red or wild pointer, we just make it wild. Okay? So that's how we infer pointer types. The next step is to infer bounds. That means for pointers which are arrays, we need to find the count or like bounds annotation. So to do that, we use a variant of correlation analysis. Basically, for each pointer, or rather for each array pointer, we associate a bound, and then we propagate this bounds information along the program. And then if the bounds propagate consistently, then we use that as the bounds for that pointer. Let's look at an example. So for this, we create two graphs, pointer flow graph and scalar flow graphs. So basically, these two graphs keep track of flow of pointers and flow of scalar variables within the program. So once we create those graphs, the first step is to figure out the seed bounds. So these are the bounds that are given to us by the programmer, either through declarations or, mostly through declarations. For instance, if we have int array 10, we know that the bounds of array is count of 10, right? So we create the pointer flow graph and scalar flow graphs. Basically, these are graphs representing the flow of variables. Then we add seed bounds. So the seed bounds, for instance, here, the seed bound is given from the memset. So from the declaration of memset, we know that the first pointer or the first parameter should be an array, and the size of it is given by the third parameter. So we add that seed bound as at the bottom as byte count. And then we propagate this information along pointer flow graph and scalar flow graphs. Once we propagate it, we find the common variable where the bounds get propagated, and we see if the variable is within the same program scope as the pointer, in which case that becomes the bound. Okay? And then once we figure out the bounds, we do the rewriting. This is what the final code looks like. But just doing the regular correlation analysis does not work always. We need context sensitivity, especially when there are structures. So here in this case, if we do not use context sensitivity, we might wrongly infer bounds of an array member to be an IDX. But if we respect context sensitivity, then we would correctly infer the bounds to be n, which is actually the bounds. So in there could be other cases where we might not infer bounds, in which case we use certain heuristics. The first heuristic is consistent upper bound. So here we observe that is there any variable which is always checked when we are trying to access? If there is always a consistent variable that's always the upper bound, we consider that as the bounds of that array variable. So similarly, we use certain heuristics based on programming patterns. For instance, name prefix heuristics, it checks that if there is any other scalar variable which has the same prefix as the pointer variable name, then we consider that as count bound. And similarly, there is a next parameter heuristic that takes the next parameter as the bounds for array parameters. Okay. So this is an example in BSFTPD, where, as you can see, index is an index into array pin, which is always checked with in length, which is the in-scope variable of pin. Our current consistent upper bound heuristics infers that the bounds of pin is actually in length. Good. We figured out the bounds. What happens to the cases where we are unable to figure out, where we are unable to convert? So for pointers for which we are unable to convert, we find the root cause. The root cause is a pointer which has been directly made wild. Here in this case, for the target pointer k, the root cause pointer is actually I, because that's the pointer which is made wild directly. And the wildness propagates from I to k. So I is the root cause for pointer k to become wild. So we give these root causes to user with the proper reason, saying that, hey, this pointer is wild, please fix it. The way we do it is we integrated this into LSP server. So these are the reasons we give to the user, and user can click on them and go to the corresponding code. And we provide some automated fixes, but user can make their own fixes if they don't like our fixes. Once user fixes this, and they can rerun 3C again, so on and so forth, until user is happy with the converted code. So to evaluate, we took 11 programs from 11 real-world programs. These are programs suggested by CheckC team, and they contain good mix of complex programming patterns that cover most of the weird uses of C. The automated part, or at least one run of 3C, took less than 1 minute on all of these programs. Note that these programs are very big, okay? They're not toy programs. We are talking about libarchive, which is like 146,000 lines of code. So 3C, like one run of 3C, took less than 1 minute on all of these programs, on each of these programs. Furthermore, most of the time is spent in getting the AST. There's a setup time, and all the other phases are just very, very fast. So our type inference, we were able to convert 67% of the pointers to check types. But if we do not split the wildness, or rather if we do not use two graphs, then our accuracy would have dropped by 20%, which is shown by the third column, 48%. Okay? And if you do not create two different copies for parameters, then the detection rate is actually now dropped by 6%. So this shows the effectiveness of maintaining two different constraint sets and maintaining two copies of constraint nodes along parameters and return types. And for the pointers where the conversion failed, when we analyze the root causes are actually very small. For instance, for the large, like 32% of the pointers we failed to convert 32% of the pointers. However, the root causes for them are just 91, and the most contributing root causes are listed at the end of the slide. So here, these are basically the things we should work on. So these are the things that tell us what the future research should be on. Okay. And for the bounds, we were able to infer 77% of the arrays. And note that for most of the bounds, our automated technique was able to infer, and heuristics only contributed to a minor percent, like 1.9%. Okay? And the detection rate is a bit less in empty array pointers or null terminated arrays. Kind of makes sense because developers don't usually use bounds variables for character arrays, for instance. And for the interactive conversion, we converted 3 programs in an interactive way. And we used a 3-phase approach. We did not have the complete interactivity implemented back then. So it was just mostly manual runs. So we ran once, we fixed the code, we ran again, so on and so forth. So here, most of the manual changes were still annotations. And we also converted a bunch of other programs which are available online. And the code, the tool is actively maintained, it's actively developed. Now it has the language server protocol interface, so you can use 3C with any of your favorite editor to convert C to checker C. Yeah, I'm ready to take questions. Thank you.
Questions?
Okay. Did you evaluate the performance of any of those libraries that you converted to see if what the overhead was?
I think we did not. We ran them to make sure that all the tests passed. We did not evaluate the performance. Our intuition is like the performance will be low based on the previous experiments, but no, we did not.
Maybe as a quick follow-up, do you have an estimate? When you say low, do you mean like 10% overhead or 50% or something?
10% is 10% was what reported in the original implementation, but the FreeBSD kernel port, it reported no overhead. Basically, they observed no overhead. So thank you.
I had the same question he did, so.
The question is, what if you're wrong about that heuristic where you took the integer in the struct to be an indicator of the size?
Yeah, that's right. So we have a mode in 3C where you can just disable the heuristics and run. So yeah, in which cases, we do actually have a report saying that which are the pointers that were inferred through heuristics. So developer can actually fix them. But you are right. Yeah. So there is always.
I have a different answer to that question.
The thing that's great about this approach is that the 3C is not trusted. You always run the check C type checker after you're done. So you will infer all the annotations. If you got it wrong, check C will reject your program, and you have to fix the annotation.
Yes, so if I understood correctly, there is still some runtime checks. So if you infer bounds correctly, can it maybe have some unwanted crashes that will not happen in the real C code?
Yes. So runtime checks, as of now, they just do halt. Basically, they terminate the program. Yeah, we can modify it so that to resort to known error cases or some kind of error handling.
Yeah. Thanks.
I'll ask one last thing. So can you say a bit about when you can't convert wild pointers? The future work, basically?
Oh, okay. So for instance, here in this case, most of them, actually the majority of them, okay. So the major reason is actually this macro expansion. So we faced a bunch of issues just rewriting macros. We want to rewrite the code to be maintainable. So if a pointer is in macro, since we cannot rewrite it, we just make it wild. So that's more of an tool issue rather than it's like a technical issue. Yeah.
And I think actually generics are a thing that would help a lot. The example that that Arvind showed, where you converted the stuff on the left to this refactoring you had to do on the right with buffers and so on. That's another example where being able to associate bounds with pointers that you take an address of is something that check C limits. And so you end up having to make your own sort of buffer like this, where you associate the bounds with the buffer, basically a C++ style string. And check C doesn't support that, so you'd have to refactor to support those things. That's another big source of errors.
All right, let's thank Arvin again.